Block 1 is sliding towards block 2. As they collide, the two blocks get stuck together. What is the final velocity of the two blocks? So what's happening here is we have this smaller block of mass m1, and it's traveling faster than this larger block of mass m2, and they're destined to collide. And when they collide, they'll look something like this. This will be the smaller block, and this will be the larger block just here. And you better believe that they do get stuck together. Let's say there's glue here between them, or let's say there's magnets, or for whatever reason they do get stuck together, right? This is something you just need to accept, and it's something that's difficult to accept, and I'll mention why at the very end. So the first thing you want to do to solve this problem is to draw a free body diagram, right? And the free body diagram for the first block will look like this. You're going to have your force due to gravity, which will be m1g, and you're also going to have a normal force. I won't bother solving it, I'll just write it as n1. Now, will you have friction? Well, because this is ice, typically that means we neglect friction. This thing slides without friction, so I'm not going to draw friction here. But there is a horizontal force. Notice if this smaller block is colliding with this larger block will start pushing this smaller block towards the left. So there'll be a internal force, which I will call F here, and that's due to the collision alone. That's all the forces on this smaller block. Let's draw the forces on this larger block now. Well, this is our larger block. We also know, just like before, we've got a force due to gravity, which will be m2g, and we have a normal force, which I'll call n2. Are there any other forces? Well, we neglect friction, but there's still that internal force just here. And from Newton's law, we know it's going to be equal and opposite, so it's going to be F just here, right? So these are two independent free body diagrams of both of our blocks respectively. And it seems like there's no way to solve this problem. It seems like we don't know the velocity of this block unless we can figure out what F is. And F would be difficult because you betcha it'll be a function of time. So it seems like I've drawn you down a dead end and there's no way to solve this. Rest assured, there's a way to get around this problem. What we can do is, rather than view the free body diagram of each block individually, what we can do is we can draw a free body diagram of our system as a whole. So this is our system just here. This is our system. And we can draw a free body diagram of our system as a whole and see if that helps us. So here's our free body diagram. I'll draw it downwards to make some space. Right? And of course, you're going to have, let's see, what are the forces on your entire system? Well, you're going to have a combined force due to gravity, which is going to be m1 plus m2g. And you're going to have a combined normal force, which will just be n1 plus n2, right? But notice, the beauty of viewing this whole system is that we don't need to include our force F here. Right? I mean, we could if we wanted to, but because they're internal forces, I'd be drawing a force here towards the left and a force here towards the right, and they'll cancel out perfectly mathematically, right? This is the beauty of drawing a free body diagram of the system. We don't even need to account for the internal forces between the collision. All we need to do is account for every external force, okay? The internal forces just cancel out. Okay, so in fact, because there's no external forces in the x direction, so because there are no external forces in the x direction, so just for clarification, I'm using my standard xy just here. Because there are no external forces in the x direction, conservation of momentum applies in the x direction. Okay, this is a proof from a previous video, but this is the gist of the conservation of momentum. Notice conservation of momentum doesn't apply all the time. It's only if there are no external forces that it applies. If there was friction, then you couldn't apply it. If there was wind blowing on them, then you couldn't apply it. It's really a specific case, so really make sure that there are no external forces on your system before you do this. Okay? Now, let's recall the conservation of momentum formula. We know the sum of momentum of each individual particle before collision, so GI before, is equal to the sum of GI after. So basically the sum of momentum of each object before collision equals the sum of each object, the sum of momentum of each object after collision. And if we were to apply this in a simple one-dimensional case, it would be, let's see, the momentum before collision is the momentum of this one, which is going to be m1 v1 plus the momentum of this one before collision, which is going to be m2 v2. In case you're confused, guys, momentum is just mass times velocity. That's what I'm doing. This is the momentum of the first particle before collision. This is the momentum of the second particle before collision. That's all I'm doing. I apologize if I'm rushing ahead. And now let's do the sum of momentum after collision. Well, we've still got two blocks. It's going to be m1 times by its new velocity, which I'll just call v prime. That's the momentum of this smaller block after collision, plus, let's see, m2, this is our larger block, times by v prime. It's the same v prime, right? Because they're stuck together. That way they have to have the same velocity, right? So this is our equation, and now we can solve this by plugging in these values. Well, on the left, you're going to get, let's see, I'll just do it in orange just here. This will be 2 times by 4 plus m2 times v2, which is going to be 3 times by 3, 3 times by 3, so 3 times by 3, and that's going to be equal to, let's see, we can suck out the v prime, and that's going to be, let's see, m1 plus m2, which is 2 plus 3, which is going to be 5, And if you solve for that, that's going to be 17 on 5. So that's going to be v prime is in fact just 17 divided by 5, which is 3.4 meters per second to the right. Okay, so that is our final velocity of both of our objects after collision. Now, I promised you I'd briefly talk about this glue in a little bit more detail, and it's actually quite interesting because you might object to the idea that they will actually stick together on the conservation of energy principle. You might say, well, hey, I've done conservation of energy, and I know the change of kinetic energy plus the change of potential energy is equal to 0, and if I apply this through, I can show that they don't in fact move together, and they in fact have different velocities or whatever. Right? And my objection to that would be, you're applying the conservation of energy formula wrong. In fact, if you were to apply the conservation of energy formula correctly, you would have the change in kinetic energy plus the change in potential energy is equal to your work done by non-conservative forces, right? And I really don't mean to confuse you guys. This is just for those special students who really want to understand this topic in a lot of detail. And in the work done by non-conservative forces, that will include the work done on the glue to deform it. So in fact, this term is not 0. And as a result, you can't apply conservation of mechanical energy here. Okay, so that's why this doesn't apply. So don't try solving this using energy methods. You'll get the wrong answer. And that's because you didn't account for the deformation of the glue. And heat and all those other energy losing aspects of the collision. Okay, I hope that made sense, guys. This is your answer. More videos on the way.